Okay, so the idea of this video is we're going to look at all of the different elements that go into a really good physics report, and in particular, how to turn non-linear data into linear data to find the equation for that non-linear data. To start with, we need to write an aim that asks us about the relationship between two different quantities that we can measure. For this example, we're going to have a go at the length of a pendulum and its period. So the first section we need to write after that's the method, and the method is where we make sure that we're including enough detail so that someone else could pick up our report and be able to repeat our experiment, get roughly the same conclusions that we got. The first part of the method is to tell what the independent and dependent variables are. The independent variable is the thing that we change. We're changing the length of the pendulum, so that's the independent variable. The dependent variable is the thing that we measured. But thinking about this simple pendulum experiment where we change the length and measure the period, in order to get that really accurate, we're not going to measure the period of just one swing. We're going to time 10 swings. And so the dependent variable was the period of 10 swings, as we can see there in our method. After that, we need to think about our accuracy improving techniques, and there's 5 main ones that we can choose from. Repeating and averaging is the thing that we should always do, because that's going to help eliminate random errors like human errors starting and stopping the stopwatch. And so you can see there we've put down that we're going to repeat 3 times for each length and find an average. The other accuracy improving technique that really applies to this experiment is multiples and dividing, and that's where, because the period of one swing is quite quick, we're going to measure 10 swings instead, just to minimize how much the human error plays into that. Other techniques we could have used were zero error elimination, parallax error elimination, and correct scale selection, but they weren't as applicable to this experiment, so they're not in there. Next up on our list are controlled variables. Controlled variables are absolutely critical to doing good science, because with good science we want to change just one thing at a time, keep everything else the same, and see what happens. And when we want to control a variable, in order for someone else to be able to pick up our method and repeat our experiment, we don't just want to say what we controlled, but we want to say how we controlled it by giving its value. You can see that in this experiment, I kept the swing angle exactly the same because I marked a 10-degree mark and made sure I always started the pendulum swinging from that 10-degree mark. I also used the same pendulum bob all the time. I used a little hexagonal nut. I put it on the scales and it was 32.15 grams. And so anyone can use the same variables as me and get the same results. And so there it is all together. That's what we need to have in our method: the independent variable, the dependent variable, the accuracy improving techniques that we used, and the controlled variables. Remember, the method is just describing what you did. You don't have to explain why you did it. Save that for later. Having got that method set up, we're now ready to have a look at our results table. And probably in real life, you'll actually end up doing the method last, and you'll end up doing this results table well before you get around to writing down how you did it. So you can see that for a good results table, right on the left-hand side there, we've got the length, the independent variable, we've got a unit for it, meters, and we've put an uncertainty, which was plus or minus 1 of whatever the smallest interval on the scale was. Just to make my repeating and averaging really easy, I've used the same heading running along the top there, period of 10 swings in seconds, that's the unit, and I've put an uncertainty, plus or minus 0.01 seconds, that's the smallest interval on the scale, and that applies to my 3 trials and the average. Final column we'll come to in a moment when we look at how to change 10 swings into 1 swing. Next, I'm going to train my spreadsheet to calculate the average for me, and you can see there I've popped in an equals average equation, and that's going to be in there even before I put the data in, and that's going to calculate all my averages for me. Then I'm going to do the same thing for my period of one swing in seconds column and have a divide by 10 equation in there. It just takes the average time and divides it by 10 because presumably the period of one swing is a tenth the period of 10 swings. Notice I didn't have to put an uncertainty on that period of one swing because it's not raw data. So we do the experiment and there are some results. You can see I didn't go up in even steps. I started at 0.1 and worked my way up to 1 metre, but my results were grouped closer together at first and then they spread out further and further as I went higher and higher. And you can see that the spreadsheet has done its job. It's calculated up all my averages and period of one swing for me. So now we can highlight the average of one swing column and the length column and plot them up on a series graph like that. I put a little bit of time into making sure that my axes had the correct labels on them that have a quantity, length in the unit meters, period, seconds, and I've added a line of best fit which nicely fitted all my points, and it's exactly what I would have drawn if I'd done it by hand. If I wasn't happy with that line, I would have just printed this off and drawn it by hand. Looking at the shape of this graph, I can recognize that that must be a square root graph, and so I'm going to assume that it's a square root graph, and I'm going to use that to change it into a linear graph and see if I'm right. To make a quick reminder of all the different graphs we've got, I jumped onto fooplot and plotted some up. First up was the square relationship. So if the graph kind of curves up like that, we think that's probably a square relationship. And so when we come to transform our data, what we're going to do is grab all of the independent variables and just square them using our spreadsheet to do that job for us. Another possible graph, this one looks familiar, is a square root one. And so if we recognize that kind of curve getting less and less steep, we would use our spreadsheet to square root all of our independent variable, all of our x variable, whatever's plotted on the x-axis by using either the equals sqrt or the just doing to the power of a half. So the next three types of relationship are confusing because they all look really similar. They all start off almost vertical, have a curve, and then go almost horizontal, noting that neither of them actually cuts either the y or the x-axis. That first one's an inverse relationship. That means we'd have to do everything to the power of -1, all of our independent variables to the power of -1. The next possibility, looking almost identical, but still not cutting that x-axis, although it looks like it does, that's the inverse square relationship. So we need to take all of our variables on all of our independent variables on our x-axis, and we'd have to do them to the power of -2, which is the same as dividing by the independent variable squared, to the power of -2. And the final one is the square root relationship, which once again looks really similar. It's just even more like it's cutting the y-axis, even though it's not, and not quite as close to the x-axis. And so to do that one, we have to do our independent variables to the power of -1/2, or to the power divided by the square root of the power. Because our graph looked like a square root graph, I've set up the results table to square root all of the length variables, which is my independent variable for me. And you can see, looking at the formula I've done there, I've done to the power of a half. If it was inverse square root, I need to be really careful with my brackets to make sure that's exactly what I get. And then if I take that new transformed independent variable on my x-axis and the old unchanged dependent variable on the y-axis and plot them up, I get a beautiful linear relationship like that. And that's really useful because I can use that to find the equation for my original data. What I've done is I've got the spreadsheet to put a nice linear trend line on there for me, and then I've got it to display the equation, and I can see that it's telling me it's a y equals 2x plus 0.00375. And so I'm just going to use my own knowledge of what we've done to the x-axis to make that a t equals 2 root x plus 0.00375. Then the final step is to take that information and pop it into my conclusion. And you can see there in my conclusion that the first thing I've written is the type of relationship. It was a square root relationship. And then down below I've popped down the equation that I wrote for that non-linear data, the 2l to the power of a half plus 0.00375 equals t. We're going to have a wee look at the things you need to do when writing a discussion. First up on the list is controlled variables. What we need to do is explain why those variables needed to be controlled. A really nice way of doing that is to explore the contra. What that means is having a think about what would have happened if we hadn't kept those variables controlled. And so for our simple pendulum experiment, from a little bit of research, we found out that keeping the size of the swing, the angle of the swing, small was really important for the experiment. And so what we could do for the discussion is have a look in a little bit more detail. What would have happened to the period of the swing if we hadn't kept that angle of swing constant? What would have happened to the period of swing, say, if we'd let the angle get bigger and bigger and bigger? Would the period have increased or would it have decreased? We'd explore what is the effect on the dependent variable. Next up on the list is a point about difficulties encountered when making measurements and how we overcame those difficulties. That's nudging us to describe the accuracy improving techniques we used, how they worked, and how they made our results more accurate. If we were thinking about, for instance, our repeating and averaging, we could write that every time we measure the period, there's a human judgment error that occurs when we're starting and stopping the stopwatch. That's a random error. We don't know if it's going to make the time bigger or smaller. And so that means that the average of our repeated variables is more likely to be accurate than any one-off measurement. So by saying that, we've explained how our technique made the results more accurate and why it needed to be used in our experiment. The next point is about the limit of the range of values we chose for the independent variable. So that's inviting us to think, why didn't we go any smaller than 10 centimeters for the length of our pendulum or any greater than 1 meter for the length of our pendulum? And we're really trying to force ourselves to think about, like, physically, why were there limitations on that? And the pendulum's not a great example, apart from like technology and that we can't do it. There's no reason why we shouldn't have made our pendulum longer and longer and longer, or shorter and shorter and shorter, except that perhaps as it got really, really short, the length of the string compared to the bob would become insignificant. And so we'd have to think about where's the center of mass of the bob rather than just considering it as a point mass hanging on the end of the string. Next up, there's a point about unexpected results. And that's not so much expecting us to consider outliers as points that don't follow the trend. Perhaps when we made our curvy data straight, there was still a curve on one end or on the other, which suggests that at those limits, perhaps there was another physics theory that was applying and that our theory doesn't apply at those extremes. And lastly, there's a point about comparing our findings with physics ideas. This means we've got to go off and do some research and find a theoretical equation that describes the same phenomena that we were investigating. So if it was a simple pendulum, I'd go off and find that t equals 2 pi square root L upon g, and by looking at that equation I would be able to determine that the theory of a pendulum is that it's a square root relationship, the same as what we got, and I might be able to work out that the gradient of the graph should be something like 2 pi over the square root of g, 2 pi over the square root of 10, and I could compare that with the value I got and see whether or not the two are in agreement. So for comparing the theory, compare the type of relationship and the values with a theoretical one.